Hello community, so great that you are back. Let's talk today about the illusion of intelligence because we found out we detected a glitch that is breaking modern AI. So welcome to my channel, Discover AI, and let's start with 6 beautiful new AI research papers that were published here in the last day. Harvard Medical School, MIT, Google, Princeton, ETH Zürich, UC Berkeley, Nvidia, Microsoft, Harvard, California, Tsinghua, and whatever. So, those 6 papers that I selected from more than 400 papers do have something in common. Let's have a look at this. First paper is by Harvard Medical School, MIT, and the Broad Institute of MIT and Harvard. And they argue why the chain of thought fails in clinical text understanding. And they say, you know what? Those benchmarks are nice, but we go out in the real world. We want to go here in a hospital, and we want to have with real electronic health records. And we want to apply AI to the real world documentation. So let's do this. And they evaluated 95 LLMs on 87 real world clinical tasks across 9 different languages. And they said, let's have a look. How good are those systems in zero shot or chain of thought? And they ask you for a step-by-step rationale before their final answer. Now I'll give you the result because the top line finding is stunning. They say that chain of thought degrades the performance for 86% of all the models that they tested. Now, you would have guessed, like I would have guessed, that the chain of thought increases the performance because this is what everybody tells us, no? Now, unfortunately, if you go out in the real world and you do the real world test, it is completely different. And they conducted here a forensic analysis to find out why. And here we have it. So you see here on the x-axis here, the release of the model here from mid of 23 up to November of 25. Yeah, nothing released yet. Of course, we are in September. And you see here in green the zero-shot performance and in red the chain of thought performance here on their medical data set from their hospitals. So this is a real world performance. Have a look, choose your result here, choose your model that you like, and you will be surprised. So what they did, they found out that longer reasoning is harmful for our LLMs. So they measure the length of the chain of thought trace and find a clear negative correlation. Because the longer the model thinks, the more its accuracy drops relative to the zero-shot baseline. So this suggests here that longer chain of reasoning introduce more opportunities for error, in particular hallucination. Then they found there's another problem that we have to face, a poor grounding in the medical concepts, because the model reasoning is not anchored to the clinical facts in the source text, in the human query. And the idea was simple, no? The UCSC takes here a clinical text analysis tool to extract simply the medical concepts from both the human input text, the query text, and the model reasoning traces. And then they go with multiple metrics, but you just calculate an alignment metric. And you just look, hey, are there medical concepts here that I put in as a human in the input text also in a model reasoning trace? Or are they missing? And if they are missing, you know, the LLM is doing something else. Plus, they found out that those LLMs, that incorrect answer were disproportionately associated with numbers, units, and clinical abbreviation. Now, this is something you do not want to see in your LLM, because this shows you clearly that your LLM is brittle with the very things that require here precision in medicine. You want to have here your medical doses in milliliters absolutely precise. And you don't want to get incorrect answer because you have some numbers, units, or numerical information in the output of the LLM. And they used the judged as an LLM to classify the errors in the reasoning trace. And you know what? They found that the hallucinations, so just inventing some facts here, and interestingly, omission, so just ignoring some critical information that is given, were the dominant failure mode in our set of LLMs. Let's jump to the second paper. And the second paper is now by Google DeepMind and Princeton University. And they did not went here to the hospital to look for this, but they went exactly the step before you go to the hospital and you have a problem. And they say, hey, can an AI system perceive physical danger and intervene? So what about the physical safety? Can an AI understand that the human maybe is encountering a dangerous situation where the physical safety is in danger? And they said, hey, how well do state-of-the-art foundation model understand here common facts about the physical safety? That a box may be too heavy to lift, or that a hot cup of coffee should not be handled by a child. And they were especially interested here in multimodal safety. And they wanted to understand, hey, what is the reasoning? Where's the reasoning going on in a multimodal safety AI, multi-agent system? And this was beautiful. And they argue, as AI moves now from chatbots to from text-oriented chatbots more to robotic or smart classes, if you have already bought one, a new, more terrifying category of risk emerges. It can cause physical harm. And the authors now argue that existing AI safety research is fixated on the digital harms. And yeah, digital harms, okay, you have bias, you have misinformation, but are we really prepared for an embodied AI? Could an AI just fail analyzing physical harm? And they developed here the Asimov benchmark, the Asimov 2.0 benchmark, and this is here a test for physical safety sense of our AI systems. And they derived this also here from real-world sources. And now you see the common topic here in the paper I present to you. It's not synthetic benchmark. It is not synthetic coding. It is about the real-world sources. And they went with the US National Electronic Injury Service and beautiful, yes, great. Give you an example. They have 3 categories. They have here the textual model, injury, A. Okay, then you have the constraints. Then you have here text and images. And you say, hey, any problem? And then you have Asimov video. And you see here this video sequence of a child, and you see exactly what the child is doing. At what time will the AI analyze there is a danger, there's a physical harm possible for this human? When will it sound the alarm? Or does it detect any problem at all? So where are we? Text, image, video, multimodal, beautiful. If you want to have it a little bit more detail, so Asimov injury is a text scenario, Asimov constraint is given an image and some embodied constraint, will it respect the constraint, and Asimov video is, as I've shown you have given me a video frame or a video sequence here with a dangerous situation unfolding. Can the AI model, the robot, or just here a visual system identify the risk and crucially determine where is the last possible moment to intervene? Let's have a look at the result. So injury, this is textual. And here you have the severity accuracy, high as better, and the risk recognition accuracy. And you see GPT-5 Mini is unfortunately really, really low. Interestingly, GPT-5 Nano is much better, and GPT-5 is, of course, okay, from those 3, GPT-5 is the best one. But look what other models can achieve. Interesting. Or understanding here action effects. No, we see the same kind of idea, GPT-5 Mini here, GPT Nano, GPT-5, but look at the other models, what they can achieve. But let's go to video, because video is really interesting. Let's evaluate this on the video performance data. And you might say a Gemini 2.5 Pro, okay, so in blue you have the text, and here in orange you have the video, and it's say, okay, yeah, 5 percentage point, yeah, risk recognition accuracy. But look at GPT-5. You go from a beautiful .92 to a horrible .52 if you have video. And triggering the intervention, we also see something interesting, no? So there's a huge difference between our models. So whatever model you will use for your robotic system or your vision action system, be aware there's massive problems ahead. Now, what are the results of the study? VLMs are far better at identifying risk in text than in video. I just showed you the numerical data. For GPT-5 and Claude, there is a 27 to 40% accuracy drop when moving from a textual description to the pure video data input, revealing a critical weakness in the dynamic visual understanding of our best models today. And we're not talking about a tiny 3 billion open source model. And those models fundamentally struggle to reason about the physical constraints. Even the best models, go with Claude or GPT-5 or Gemini, have constraint violation rates up to 75%. Now, there's something positive, and the authors show that providing models here, also smaller models, smaller 70B models with more inference time compute, give them more thinking budget, more time to think, more complex system. This really improves the safety performance of our vision language action models or vision language models. This is great. So, more power, more time to think. And they demonstrate what is really what's the missing piece, what is really a solution. Take a baseline model, fine-tune it on a very specific action characteristic small data set of just 200 examples with structured reasoning traces in our multimodal system. This will dramatically outperform all other, even the biggest model with trillion free trainable parameters. This shows us those systems have not been trained properly for physical harm. Maybe for a syntactic textual benchmark, but not for physical harm. So this shows that teaching those models, and now we have to invest and teach those models how to reason about physical safety in a structured way, is much more effective and maybe a solution also for smaller models, or the other way would have been simply scaling the model up to 1 trillion of free trainable parameter. But this study shows us it's not necessary. You just have to train it better. Now let's come here to Google DeepMind, ETH Zürich here. And they say, you know what? Since we understand that this learning process is so important, is it possible that in this learning there is some shortcut? That learning is not happening, but there is something bad happening. So they said, let's have another test set about a vision language understanding. Yes, we are again multimodal. And they say, diagnose if there's a shortcut in the learning. Are there some mistakes? Are systems not learning at all? And they say, hey, the recent evaluation here on the syntactic text only suggests that vision language model perform well. And they focus now on a diagram. They say, if you have here a visual diagram, there are benchmarks and they are great, and those benchmarks are known for years and the diagrams are known for years, great. But what about we go out in the real world and we have a look at the reasoning and the modality shortcuts, whether the models really understand what is happening and are they really reasoning over the information in the diagrams, or are they using just shortcuts and not looking at the diagram? And they say, VLMs, if you look at the test, at the current syntactic benchmark, hey, they're real good, no? But let's look at the real time. And they said, hey, let's be skeptical and let's go to real world data for visual reasoning. And they designed here a CHIMERA test suite. And they said, we built a diagnostic toolkit, not just another leaderboard. And now, honestly, it is beautiful. This CHIMERA, they said, you know what? We go now to the theory of semiotics. Absolutely gorgeous. So the study of signs and symbols, and build on the semiotic insights that we have. It's a branch of research, of course. We will build now a complete different test suite, a complete different benchmark to have a deeper understanding if true visual reasoning is happening at all, and if, to what extent. So they said, okay, let's have 3 different modalities to see how the model performance will change. And you know what? It will change dramatically. And I said, okay, we have here a diagram from Wikipedia and we have a visual modality. Great. Then we have, of course, a textual modality. Sentences derived from the triplets representing the information in the format LLMs are most comfortable with. And then we have a semantic modality, a clean structured graph representing the core information as a semantic triple. This removes the visual noise and ambiguity. I will show an example in a second. And then I said, let's create 4 tasks with increasing cognitive complexity, like human semiosis. And I said, let's start with the entity recognition. Can you identify parts, anything? Relation understanding. Can you understand how the parts here are connected in our diagram? Knowledge grounding. Can you link the diagram to outside knowledge? And the visual reasoning, finally, can you infer new information? So absolutely beautiful to go back on semiotics. I've never seen a test on this. And here, if you want to see it, here the visual modality where you say, okay, this is it. Then you have the semantic modality and the textual modality. And then you have the 4 tasks I just mentioned, the entity recognition, the relation understanding, the knowledge grounding, and the visual reasoning. And they said, you know what? And now let's do the test. And they said, we are looking specifically for 3 types of cheating. The vision language action model could be cheating. And we know it is possible because we recognized it. But let's do it here in a beautiful categorization. Let's analyze it scientifically. So the first shortcut to cheating here is a visual memorization shortcut. Does the model just recognize a familiar image from its training data? Was it in the training data set? Second, the knowledge recall shortcut. Does the model bypass the diagram entirely and just answer from its vast store of pre-trained knowledge, not looking at the diagram at all? And of course, what they call here the clever Hans, I think there's a German history behind it, is the model completely ignoring the image and just exploiting the linguistic pattern in the question and in the answers and in anything in this conversation that went beforehand. And I know what you think. You think, no, there is no shortcut. Our vision language models are just perfect, no? Okay, so let's do the tests. So what were the results? There's a lot of additional data in the paper. Have a look at the paper. I just give you the results. Shockingly, our vision language model performs slightly better on noisy real diagrams. So this simply means that they are exploiting here memorized visual patterns rather than a real reasoning from the underlying structure because it's really noisy. And the performance difference is only there, but it's a red flag, no? And I said, model perform about 5% worse on simple entity identification than on complex reasoning task. This is a clear sign that they are recalling the answers from their knowledge, from their inherent knowledge, rather than seeing the diagram at all. And you have to look at the real publication because there's a lot of additional testing going on. I just give you here the main result. If you want, have a deep dive yourself. And I think the most significant shortcut of all that those found is that the models achieve substantial non-trivial accuracy without no visual input at all. So you don't give any input at all to this vision language model and it has a great accuracy, proving that they rely heavily on the linguistic prowess and not on the visuals. So what does this tell us about the performance of vision language model? The vision part is hardly there. So here you have it now. 3 beautiful studies all published here yesterday, 26th of September, and this is, the day before yesterday, 25th of September here. Harvard, MIT, Google, Princeton, ETH Zürich, Google, DeepMind, and so interesting to see. And now let's look at those 3 papers because I selected them for you in a specific way. They go all beyond benchmarks as leaderboards. They are now really scientific instruments, like a macroscope, like a macro probe. And they are specifically designed by the universities to really dissect the model behavior and reveal the hidden mechanisms of reasoning and show us the mechanisms of failure, when and how and because of what failure is happening. And we need to understand this to improve our models further. So CHIMERA uses here the modality shift to do this. The clinical paper, our first paper, uses the domain stress testing, and the Asimov 2.0 benchmark uses here the real-world physical grounding. You see, we are moving away from synthetic benchmark to real-world experiments. We are entering an era where the most valuable research will not be about building a slightly bigger model, GPT-6, that inches up the leaderboard, the synthetic leaderboard on non-real-world data. But we have to understand why our models today fail on real-world data. So we need to understand, we need to reveal a new class of failures that are not documented, that there's no documentation here by OpenAI, for example, because they are heavily proprietary and closed systems. But we, as a scientist, we need to understand what is happening, and hopefully those open source systems, they will provide the answers that are valid for all vision language models. And you see, the central challenge is no longer, hey, can the LLM or VLM or VLA do the task? Is it successful? No, we are not interested in this. We want to understand how and why does the VLM succeed or fail, and what are the particular failure modes. And unfortunately, the global corporations are not providing any open source reports or publication about this. And therefore, it is so important to have here the teams at the universities and also, as you see, Google, MIT, who do this analysis. Because we will desire interpretable reasoning models. But as the clinical paper provides here a stunning counterpoint, forcing a model here to reason in a medical domain it does not really deeply understand can be more dangerous than a simple direct output, because it is hallucinating and omitting and. So here at the end of September 25, this is a brutal callback to reality in AI. And the solution is, of course, not to abandon here the reasoning here, but to understand it, to tame it. And I think the Asimov paper, and this is why I wanted to show you this Asimov 2.0 benchmark, they have success with the post-training here on very domain-specific structured reasoning traces. And they found out, hey, this could theoretically, maybe, hopefully, provide a way forward. So, we have to understand why we fail, and then we have to find new solutions. I give you an example here. I had to laugh about this, sorry. If you ask an AI doctor about a patient with a fever and a rash, and the zero shot is the heuristic, hey, it could be what is, if you go for pure statistical data, it could be measles, fast, and maybe this is right, nobody knows, And then you have your chain of thought, and this could be really dangerous, and this was part here of the first study I showed you. And the AI says, now, let's think. And you might think, hey, chain of thought. So this is now a reasoning system. I can trust this system. But look at the reasoning traces. Fever and rash are common. Rashes can be red. Red is a color of a stop sign indicating danger. Measles is a dangerous childhood disease. Therefore, it is measles. So you see, there was a reasoning chain of thought. There was a reasoning sequence that makes sense in a very limited sense. So the reasoning was also fluent, and it was also, in a crazy way, plausible. But the logic was absolutely crazy, nonsensical, and untrustworthy. And if those are the reasoning path in a chain of thought for a medical system, this could be theoretically dangerous if you would really employ it in real-world environments. We have to improve our AI systems much, much further before we are, let's say, reasonable that we can operate with them in an alpha environment. And then, of course, it's about grounded, structured reasoning that is trustworthy. Because what you want, in the best case, is the AI says, hey, let's identify the key symptoms. Patient presented with fever, some rash, some spots, compare this against the known diseases, all the known diseases, all these systems, what could it be? Then rule out step-by-step alternatives, examine further data, request further data, and then maybe come to a conclusion. Maybe you want some other lab result, test results to be included. And then you can go with a probability distribution and have a probability-based answer what it could theoretically be. So, yeah, somehow we are far away from a solution. But those 3 papers were so beautiful, and when I saw them here, I said, I want to show you this. Because this is now finally about real-world artifacts. Wikipedia was really about real-world diagrams, the clinical was really about health records in the hospitals, and the US national injury statistics here, with the injuries that happen in the real world. They proved that to build an AI that is genuinely useful and safe to use, we must move beyond those sanitized, abstract, synthetical test beds and benchmark and confront the complexity, the noise, and the unforgiving nature of reality. Benchmarks are not enough anymore. But you know what? These failures uncovered in these controlled but realistic settings are the warning we need currently maybe to finally pay attention before we deploy those AI systems at scale in the real world, because where the consequences are no longer just a lower accuracy score in a test bed, but imagine potentially if you really deploy those systems, this could have theoretically a catastrophic system failure in the complete medical environment. So therefore, careful, we are not there yet. Okay, so these were the first 3 papers. Okay, we have paper 4, 5, and 6, but you know what? I think given the complexity and the time of the video, maybe we make here an interrupt. This was part 1, and in my next video, finally, we have a look at the next 3 papers. And then I will do a summary here of the deeper connection between all those 6 papers, but I think this will be a subject here of part 2. I say thank you for listening. If you subscribe, I see you in my next video.